Kanghyun moved from KAIST in South Korea after his PhD to EPFL in Switzerland already 4 years ago, if I'm not mistaken, where he works on piezo response force microscopy and relaxer ferroelectric materials in the group of Dragan Damjanovic. He will tell us today about some interdisciplinary approaches combining lateral DFRT and angle resolve PFM.
Okay,
So
thank you, Chair.
Yeah, thank you very much for your presentation. Looking forward.
Thank you. First, I would like to thanks to organizers for inviting me to this nice workshop. And hello, my name is Kanghyun Chu. I'm working in the EPFL with the Dragan, and today's topic is the visualization of the fine domain structure of the relaxer ferroelectrics. And this is basically collaboration of the conventional some DFRT lateral PFM and the image processing. So I'm going to guide you to the kind of backstage of what's going on behind the images. Okay, let's move on to this basic principles. Oops. So this is an outline of today's presentation. So I'm going to briefly explain you the basic principles of the PFM and the dual frequency resonance tracking technique, which is already addressed this morning, and the lateral PFM and the angle visual PFM stuff. And then I'm going to show you my work, and well, that will be more or less end of my that will lead to the end of my presentation. So let's move in. So piezo response force microscopy is basically a tool to visualize the ferroelectric domains or piezoelectric domains of the surface. It utilizes a sharp conducting tip to route a electric field to the sample, and the piezo response is induced by the applied field. It deforms the surface and it generates some force to the cantilever, and then it bends, and we can pick up the cantilever bending so that we know that, oh yes, there is some piezoelectric response underneath the tip or not. And one good thing is when we apply the AC bias, AC field to the tip, then the phase of the response is totally connected to the polarization direction of the sample underneath. So if the electric field is here going downward and expand, we can think like, okay, since the electric field applied to the downward and the sample expand, that means the ferroelectric polarization might be the downward. If it contracts, then means the electric field and the polarizations are opposite. So we can think like, in that case, it is a upward polarization. So by analyzing the phase of the obtained signal, then we can find out what is the polarization direction of the sample itself. So dual frequency resonance tracking is, as we discussed, as you heard explained this morning, it utilized the contact resonance of the cantilever. The conventional PFM was done in the low frequency limit as shown in the left image. So the cantilever motion is more or less static, close to the static response. So the tip expands, the cantilever goes up. If the sample surface contracts, then tip goes down. So the vibration mode is close to the fundamental vibration mode of the cantilever, something like a diving board. But if we increase the frequency of the applied AC, then now the dynamic characteristic of the cantilever kicks in. So not only just going up and down like this diving board, now there is kind of buckling motion comes in. And as a result, the angle at the end of the cantilever is amplified because of the kind of resonance motion. So that's why we can get a better the signal to noise ratio in this DFRT, the resonance PFM techniques. But the problem is the resonance frequency is not the same over position to position. It can change due to the material property or the scanning condition or the tip sample interface, the status. So we have to overcome the changing of the resonance frequency to get nice image. So to do so, we use the sideband frequencies to track the resonance frequency of the cantilever. So here, I draw some simple diagram of the model system. So we have the sample here, and the cantilever and the tip is sitting on it. And we can model this whole system to the simple harmonic oscillator we have learned in when we were all in the freshman. So there is some mass and the elastic constant here, the spring, something like that, and the damping factor is there. And if we write the equation of motion of that and solve the particular solution when external the sinusoidal driving comes in, we can write down a amplitude of this motion is written like there's something written in this equation. And if you draw this equation to the plot, you have some Lorentzian shape of the peak, and the corresponding phase is going 0 to the 180 degrees. So we can use this to track the resonance. So by using two side bands, one lower the resonance frequency and one above the resonance frequency, once the resonance frequency shifts like this, then the lower the sideband lower the resonance frequency goes down, the amplitude of the response goes down, and the amplitude of the response at the resonance frequency plus the center frequency plus the sideband frequency goes up. That means if we track the condition that these two amplitudes are all time the same, then we can successfully track the resonance frequency. So we can keep the resonance frequency inside this frequency window like this. So just maybe explained in the previous session, we can use the feedback control of the center frequency by using the amplitude difference from between the lower sideband and the higher sideband. So this is what we can get from the conventional PFM and the dual frequency resonance tracking PFM. On the left column, this is a conventional PFM. The sample is bismuth ferrite, and we can see some amplitude image and the phase image, but you can see that the image quality is not that clean. But at the same region, same area, we'll jump into the resonance tracking technique, then we have way better image quality, better signal to noise ratio, and clear boundaries. So that's why we use a resonance technique to get nice image. Here we applied the 2 volt for the conventional PFM, and also, which is the same for the dual frequency resonance tracking PFM. Come on. And now let's move on to the lateral PFM. For now on, I explained the PFM that work for the out-of-plane response, but similar thing can be done to the in-plane response. Instead of using the out-of-plane motion, we can use the in-plane motion to get the surface, the piezoelectric property information of the sample. But this time there is one limitation. When the in-plane motion is induced, to get that information, we utilize the torsional vibration mode of the cantilever. And since this is a torsional vibration, if the surface motion is parallel to the cantilever axis, then that kind of the piezo response cannot be captured by the torsional vibration, or maybe it can be just blended to the out of plane signal. So we cannot get that information. So only the projected component of the in-plane motion to the cantilever axis can be captured. This kind of in-plane piezo response can give you the in-plane domain image of the ferroelectric sample or piezoelectric sample. And in that case, the piezoelectric coefficient of D35 or D11 is most responsible for such in-plane motion. That means if I apply the electric field along the surface normal direction, then the shear motion across the sample generates the in-plane displacement. And for the 1-1 component case, the diverging electric field near the tip apex generates some one expand region on the one side, let's say right side, and the other side there is some contract region, leading to overall kick toward some left or right direction. So those kind of piezoelectric coefficients are responsible for the in-plane piezo response. And the angle resolved PFM is inspired by how can we integrate those kind of the projected PFM images to restore whole 2D in-plane ferroelectric domain structure. So let's see this. When we have a different orientation of the cantilevers, then each will give you different piezo signal. Here, I mean the amplitude rear part, or sometimes we often call both X or just X. So let's see once more time. So when the tip is along this side, then the torsion is torsion is a right-handed direction when your thumb direction is the cantilever axis, so that is positive. But if the tip rotated by 180 degrees, the cantilever is rotated by 180 degrees, then the sign becomes opposite. And if you follow the profile of the PFM signal, then it will give you some nice sinusoidal response. So if we have multiple lateral PFM images that obtained from various tip sample relative orientations, then we can reconstruct the in-plane piezo response map. So this is a demonstration how we can do that. So each image is a piezo, the piezo response image, the amplitude rear part for various cantilever orientations. And after aligning those images, and let's say pick up one position from all 4 images and draw a fitting, then we can assign the direction of the in-plane piezo response like this. Or maybe we can try at another spot, then we can do same sinusoidal fitting and get the in-plane direction. And if we repeat all this procedure over pixel to pixel, we can have this kind of nice vector map of the surface of the in-plane piezo response. But this is done in the conventional lateral PFM, which is work at the low frequency limit, like a 100 kilohertz or 10 kilohertz. But we want to employ the dual frequency resonance tracking to the technique, because we can have a better signal to noise ratio. And in case of my system of relaxer, it is quite susceptible to the external excitation. So even like 1 volt AC scanning might change the surface electronic structure. So I want to keep the applied bias low, but want to get the high signal. Then utilizing the resonance technique is kind of an inevitable solution to go through. So let's see. I'm going to explain how did I do this job. First, I prepared the relaxer sample, which is the PIM, PM, and PT. So I pulled the sample and prepared the cleaved surface. And I do the 4 scans of the same area of the sample. So basically, this is some raw images that I've got. I have surface images, 1 channel, and 4 channels of the dual frequency resonance tracking lateral PFM images, the amplitude phase for the 2 sideband, 1 lower, 1 higher. And along with that, I have the frequency images, the frequency map, and some initial AC tuning spectrum, which shows the initial Q factor. So these are some raw images. So I'm going to show you how to process whole images at some integrated manner. First, I crop some same area inside the images. So this red box is the one I set it by my hand. So taking the image from this red box, there the bottom row is showing that. And still there is one more step to go further. You can see that for now the image is not well aligned, but we can, with the assist of some image processing and surface feature detection, then we can find a nice conversion map from one image to the other, the coordinate conversion maps. When I was doing my PhD, at that time, I was not familiar to this kind of the surface image processing. So I have to pick up the point by point by hand and my eyes. So that is quite hard and tedious job. But now computer vision can help a lot of work instead of human power. So once there is some nice transfer maps prepared, I can align whole images based on the surface morphography. So now you can see that the surface maps from different cantilever orientations have quite nice alignments. And using the disk coordinates, we can find the corresponding maps of amplitude and phases. Here, each image has a 650 nanometer by 650 nanometers, so it's quite small area. And to analyze the low limit, so what we want to do is convert this amplitude and phase images at or near the resonance to the DC limit response. To do that, I'm going to revisit our harmonic oscillator solution. So if I draw the trajectory of the amplitude, the complex amplitude of the response with respect to the frequency, it forms a kind of quite similar to the circle. Not exactly a circle because of this term, the frequency of the resonant frequency over the applied frequency term. But the term in the back is the perfect circle. So, well, we can approximate our response as a circle. And what we have is the frequency 1 amplitude and frequency 2 amplitude, which are sideband lower and the sideband higher. And since this is a circle, we can estimate the resonance frequency, the response at the resonance frequency by drawing the circle. So we have this point, and as we go to the frequency infinity, then we'll hit the origin. So based on 3 points, we can draw a circle, and we can estimate the resonance frequency response, then this will give us a DC limit response from the relation that the DC limit is the resonance response divided by the Q factor and the phase shift of the 90 degrees. Here, the Q factor is also calculated from the phase difference between the frequency 1 and 2's phase difference, as in this formula. And since we know the frequency difference between the between two sidebands, we can now do all the job. So this is what I get. Since I can get the DC limit response, then I simply follow the procedure of the angle bridge technique, the sinusoidal fitting at point by point. So this is the resultant, the in-plane piezo response map of the relaxer ferroelectrics. If I overlay the surface image, it looks like this. And if I, instead of arrows, doing is this color plot, then it will show like this. So maybe from this image, we can find some such signature of the polar regions or etc. And we can, since we have a 2D vector map, we have some playground, and we can apply the vector operation to the field to extract some useful information, such as a divergence or curl. For example, if we assume that the piezo response is proportional to the in-plane polarization, then the divergence map will give us the charge density, the spatial charge density. Maybe they can be screened by the carriers, but the ionic, the charge distribution will look like this. And unlikely the divergence, the curve, there is not much interesting feature in this specific example. So today I introduce you how to do the DART-based, the dual frequency resonance tracking based the angle visual PFM. And this is quite nice tool for the exploring nanoscale structure of the not well defined, if you want to visualize the in-plane piezo response or ferroelectric polarization field. And thank you for attention.
Thank you very much. So that's a challenging technique. So let me ask you a first question. So
Yes.
you have to rotate not only at 0 and 90 degrees, but at different value for this lateral
Yes.
PFM. And don't you see effect of drift or creep when you have to change? Because how long does it take to make all these images so that you can reconstruct everything?
Well, it really depends on how quickly you can get the same position. In this case, it takes like 12 hours in total. Most of the time,
basically you can reconstruct because you can see some feature and
yes.
found the same feature again. Yeah.
Yes. So there is usually we have a microscopes, so we can position our cantilever close to the original place, and that will guarantee you like a few micrometers away from the original position, or maybe smaller than that. Then if you start scanning and zoom into the original place, that is most time-consuming part. And here, since we have to maintain the same calibration condition, the cantilever should not be changed when you change the sample orientation. So that is quite tricky. So all cantilever or all probes have its lifetime, and we are spending some time mostly not getting actual data set, but going into the original place. That is.
So you have some tipware that after a while So the image doesn't get the same quality anymore.
Most of case, yes, but that is the where you stop. So if the tip is nice, I can do more than 4 or 5 or 6, 7 sets. But in here, after this 4 set, now the images start to degrade it. So I stopped here for this specific example.
And from
So,
what I understood, this technique would be almost impossible without image recognition, right?
well,
Because you have so many things to align. So
yes,
many
there
things
is
to
so
make
many things to align. Yes, that's true. But we can do it by our hands and eyes. If I make a table for the coordinate conversion from one image to the other, then that will provide you nice transform to give you the transform function from one image to the other. But by using the computer vision algorithm, the workload is lower and it works more faster.
Yeah. So I see that you are reconstructing in the plane, so the vector in 2D, but you also have the vertical deflection in principle. So can you reconstruct the whole 3D, or is this something I missed?
That is in principle possible. Yes, in my talk, I did not integrate the out-of-plane motion to my 2D map, but it is possible to integrate the out-of-plane motion too. But the problem is we have to calibrate properly to the out-of-plane component and the in-plane component. If I play in the just in-plane, then the calibration factor is all the same. But if I want to address the out-of-plane, then even though our photodetector, the vertical deflection and the in-plane torsion signal, the lateral and vertical give you, say, millivolt scale the value, but that does not guarantee that actual physical dimension of the piezo response are the same. So I mean, if the, let's say 100 picometer change of the surface along the out-of-plane direction will give you a certain amount of the deflection change in your photodetector. But it does not mean that if the same amount of 100 picometer in-plane motion will give you same amount of the lateral or torsional photodetector value. So we have to somehow calibrate that at the first time.
Oh, perfect. So thanks again for this great talk.